Section 4.4 Oxidation Reduction Reactions. In precipitation reactions, cations and anions come together to form an insoluble ionic compound. In neutralization reactions, hydrogen ions and hydroxide ions come together to form water molecules. Now let's consider a third kind of reaction, and one in which electrons are transferred from one reactant to another. Such reactants are called either oxidation reduction reactions or redox reactions. In this chapter, we concentrate on redox reactions where one of the reactants is a metal in its elemental form. Oxidation and reduction. One of the most familiar redox reactions is the corrosion of a metal. In some instances, corrosion is limited to the surface of the metal, with a green coating that forms on copper roofs and statues being one such case. In other instances, the corrosion goes deeper, eventually compromising the structural integrity of the metal. Iron rusting is an important example. Corrosion is the conversion of a metal into a metal compound by a reaction between the metal and some substance in its environment. When a metal corrodes, each metal atom loses electrons and goes to form a cation, which can combine with an anion to form an ionic compound. The green coating on the Statue of Liberty contains copper-2 combined with carbonate and hydroxide ions. Rust contains iron-3 combined with oxide and hydroxide anions. Silver tarnish contains silver combined with sulfide ions. When an atom, ion, or molecule becomes more positively charged, that is, when it loses electrons, we say that it has been oxidized. Loss of electrons by a substance is called oxidation. The term oxidation is used because the first reaction of this sort was studied were reactions with oxygen. Many metals react directly with O2 in the air to form metal oxides. In these reactions, the metal loses electrons to oxygen, forming the ionic compound of the metal ion and the oxide ion. The familiar example of rusting involves the reaction between iron metal and the oxygen in the presence of water. In this process, iron is oxidized, it loses electrons, and forms iron 3+. The reaction between iron, and oxygen tends to be relatively slow, but other metals such as the alkali and alkali earth metals react quickly upon exposure to the air. Figure 412 shows how bright metallic surfaces of calcium tarnishes as calcium oxide forms in the reaction. Ca plus O2 yields 2 calcium oxide. In this reaction, calcium is oxidized to calcium 2+, and neutral oxygen is transformed into oxide ions. When an atom, ion, or molecule becomes negatively charged, gains electrons, we say that it is reduced. The gain of electrons by a substance is called reduction. When one reaction loses electrons, that is, when it's oxidized, another reactant must gain them. In other words, oxidation of one substance must be accompanied by reduction of some other substance. Figure 411. Familiar corrosion products. A green coating forms when copper is oxidized. B, rust forms when iron corrodes. And C, black tarnish forms as silver corrodes. Figure 412. Oxidation of calcium metal by molecular oxygen. The oxidation involves transfer of electrons from the calcium metal to the oxygen, leading to the formation of calcium oxide. So calcium metal is bright silver, calcium oxide is a dull gray-black. Oxidation numbers. Before we can identify an oxidation reduction reaction, we must have a bookkeeping system, a way of keeping track of electrons gained by the substance being reduced and electrons lost by the substance being oxidized. The concept of oxidation numbers, also called oxidation states, was devised as a way of doing this. Each atom in a neutral substance or an ion is assigned an oxidation number. For monatomic ions, the oxidation number is the same as the charge. For neutral molecules and polyatomic ions, the oxidation number of a given atom is a hypothetical charge. This charge is assigned by artificially dividing up the electrons among the atoms in the molecule or the ion. We use the following rules for assigning oxidation numbers. Number 1. For an atom in its elemental form, the oxidation number is always 0. Thus, each hydrogen atom in the H2 molecule has an oxidation number of 0. Each phosphorus atom in the phosphorus P4 molecule has an oxidation number of 0. Number 2. For any monoatomic ion, the oxidation number equals the ionic charge. Thus, potassium ion has an oxidation number of +1, sulfide ion has an oxidation number of -2, and so forth. In ionic compounds, the alkali metal, group 1, always has a +1 charge, and therefore its oxidation number of +1. The alkaline earth metals, group 2, are always +2, and aluminum, group 3A, is always +3 in ionic compounds. In writing oxidation numbers, we'll write the sign before the numbers to distinguish them from the actual electronic charges, in which we write the number first. Number 3. Nonmetals usually have negative oxidation numbers, although they can sometimes be positive. A. The oxidation number of oxygen is usually -2, both in its ionic and molecular compounds. The major exception is the compounds called peroxide, which contain the O2 -2 ion, giving each oxygen an oxidation number of -1. The oxidation number of hydrogen is usually +1 when bonded to nonmetals and -1 when bonded to metals. C. The oxidation number of fluorine is -1 in all compounds. The other halogens have an oxidation number of -1 in most binary compounds. When combined with oxygen, such as oxyanions, however, they may have positive oxidation states, or they do have. Number 4. The sum of oxidation numbers of all atoms in a neutral compound is 0. The sum of the oxidation numbers in a polyatomic ion equals the charge of the ion. For example, in the hydronium ion, H3+O+, the oxidation number of each hydrogen is +1, the oxygen is -2. Thus, the sum of the oxidation numbers is 3 +1s, hydrogen, 1 -2, oxygen, and it equals +1, which equals the net charge of the ion. This rule is useful in obtaining the oxidation number of one atom in a compound when you know the oxidation number of the other atoms, as example 4.8. It's important to remember that in every oxidation reaction, the oxidation number of at least 2 atoms must change. The oxidation number increases for any atom that's oxidized and decreases for any atom that's reduced. Oxidation of metals by acids and salts. The reaction between a metal and either an acid or a metal salt conforms to the general pattern A plus Bx yields Ax plus B, single displacement reaction. Examples: zinc metal plus hydrobromic acid yields zinc bromide plus hydrogen. Manganese plus lead nitrate yields manganese nitrate plus lead metal. These reactions are called displacement reactions, single displacement, because the ion in solution is displaced through the oxidation of an element. Figure 4.13, reaction of magnesium metal with hydrochloric acid. The metal is readily oxidized by the acid, producing hydrogen gas, H2, and magnesium chloride. Many metals undergo displacement reactions with acids, producing salts and hydrogen gas. For example, magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. Magnesium as a metal is an oxidation number of 0. Hydrogen is +1, chlorine is -1. The salt, though, magnesium chloride, chlorine being a halogen, is -1, so there's 2 -1s, magnesium +2 to balance, and hydrogen gas as an element is 0. The oxidation number of magnesium changes from 0 to positive 2, an increase that indicates the atom has lost electrons and therefore has been oxidized. The oxidation number of hydrogen ion in the acid decreases from positive 1 to 0, indicating that this has gained electrons and therefore has become reduced. Chlorine has an oxidation number of negative 1 both before and after the reaction, indicating that it is neither oxidized nor reduced. In fact, the chlorine ions are spectator ions dropping out of the net ionic equation. The net ionic equation 4.26, magnesium metal plus hydrogen ion yields magnesium ion plus hydrogen gas. Metals also can be oxidized by aqueous solutions of various salts. Iron metal, for example, is oxidized to iron ion by aqueous solutions of nickel-2, such as nickel nitrate. Molecular equation: iron metal plus nickel-2 nitrate yields iron nitrate plus nickel metal. The net ionic equation is iron plus nickel-2 ion yields iron 2 iron plus nickel metal. The activity series. Can we predict whether a certain metal will be oxidized either by an acid or a particular salt? This question is of practical importance as well as of chemical interest. According to equation 4.27, for example, it would be unwise to store a solution of nickel nitrate in an iron container because the solution would dissolve the container. When a metal is oxidized, it forms various compounds. Extensive oxidation can lead to the failure of metal machinery parts or the deterioration of metal structures. Different metals vary in the ease to which they are oxidized. Zinc is oxidized by aqueous solutions of copper 2 ion, for example, but silver is not. Zinc therefore loses electrons more readily than silver, that is, zinc is easier to oxidize than silver. A list of metals arranged in order of decreasing ease of oxidation, such as Table 4.5, is called the activity series. The metals at the top of the table, such as alkaline metals and the alkaline earth metals, are most easily oxidized. That is, they react most readily to form compounds. These are the active metals. The metals at the bottom of the activity series, such as the transition elements from groups 8b and 1b, are very stable and form compounds less readily. These metals, which are used to make coins and jewelry, are called noble metals because of their low reactivity. The activity series can be used to predict the outcome of reactions between metals and either a metal salt or an acid. Any metal on the list can be oxidized by the ions of the metal below it. For example, copper is above the silver in the series, thus copper metal is oxidized by silver ions. Table 4.5, activity series of metals in aqueous solutions. Anything towards the top of this list is easier to oxidize. It gives away an electron easier. Anything lower is harder to give away an electron. So it will not be oxidized. So anything below something can kick out something above it. The oxidation of copper to copper ions is accompanied by the reduction of silver to silver metal. The silver metal is evident on the surface of the copper in figure 4.14. The copper 2 nitrate produces a blue color in the solution, as can be clearly seen in the photograph on the right of 4.14. Figure 4.14, reaction of copper metal with silver ion. When copper metal is placed in a solution of silver nitrate, a redox reaction forms silver metal and a blue solution of copper 2 nitrate. The oxidation of copper to copper ions is accompanied by the reduction of silver ions to silver metal. The silver metal is evident on the surface of the copper wire. The copper 2 nitrate produces a blue color in the solution, which can be most clearly seen in the photograph on the right. Only metals above hydrogen in the activity series are able to react with acids to form hydrogen gas. For example, nickel reacts with hydrochloric acid to form hydrogen. Because elements below hydrogen in the activity series are not oxidized by hydrogen, copper does not react with hydrochloric acid. Interestingly, copper does react with nitric acid, as shown in Figure 111, but the reaction is not oxidation by copper by hydroxide by hydrogen ions. Instead, the metal is oxidized to copper 2 by the nitrate ion, accompanied by the formation of the brown nitrogen dioxide gas. As the copper is oxidized in this reaction, nitrate, where the oxidation number of nitrogen is positive 5, is reduced to nitrogen dioxide, where the oxidation number of nitrogen is positive 4. We'll examine reactions of this type in Chapter 20.